This is ExactFlat Scan-to-Pattern, and we'll show you how. In today's example, we are going to be scanning the human body. This may be for applications such as making compression garments, prosthetics, braces, and other applications that require a custom fit to the human body. We're going to be looking at a simple scan today of the arm and making a compression sleeve. I'd like to introduce Peter Warburton from PO3D. Peter is holding the scanner right now. We are going to be doing this demonstration on a human arm. And because an arm is not a rigid scanning surface, we have to set our scanner to semi-rigid object. And to do that, we just tick the box right here, just tick it semi-rigid object, and then we will set the scanner up to have an optimal result. Okay, we are now ready to begin our scan. And you can see here the body is held in a certain position, hand is on a stable surface, and this is because to get the best results, the body cannot move. It must be held in the same position from the beginning to the end of the scan. You'll come up with your own mechanisms for doing this, your own workflow, your own techniques, but the important point is the body and the part must remain in the same position. Peter's holding the scanner about 30 to 40 centimeters away from the surface of the body. And this is optimal. And you can see that when he needs to scan the underside of the arm, he orbits the scanner around so that the scanner is pointing at about a 90-degree angle to the surface being scanned. In this particular case, it's pretty straightforward and it only takes about a minute. This concludes part 1 on how to scan. In the next section, we'll show how to convert the scan to 3D CAD. Following that, we'll show how to flatten our CAD model into 2D flat patterns that can be cut, sewn, and assembled into the final customized product. Okay, let's begin part 2, converting our scan to 3D CAD. We're going to be using VX Model for this process, and I've already loaded the scanned arm into VX Model. As we pan and rotate around, you can see the scanner has picked up quite a bit of detail. Some of this detail is useful, and some can be eliminated. When considering the workflow from scan to pattern, there are 2 basic steps when we convert our scan data to 3D CAD data. First, adding detail, such as filling in holes. And second, eliminating unwanted detail, such as the wrinkly bits in the elbow. The goal is to produce a smooth surface that is useful for pattern making. The full workflow steps are shown on the right. It is helpful if we first assess and plan what we're going to do based on the scan we have. We can review the scan, define the objectives, and then plan our steps. Next, we align our scan to the origin. This is particularly helpful when we need to edit the geometry. Editing the geometry involves filling in holes, trimming and smoothing boundary edges, and defeaturing surfaces. When that is complete, we can prepare our pattern segments. We can use planes by creating planes, or we can cut the mesh to extract pattern entities that way. And lastly, we can combine mesh elements together. In the end, we save our model, and this will be used to import into our 3D CAD program. A full step-by-step tutorial of this process is provided in another video that will show exactly how we did it. For now, through the magic of video editing, we'll skip to the end result. And as you can see, unwanted detail is gone, essential detail is maintained, and we are left with a smooth surface, which is perfect for converting from 3D CAD to 2D flat patterns. This concludes part 2, how to convert our scan to 3D CAD. Next, in part 3, we'll show how to create perfectly accurate 2D patterns from our 3D CAD model. It typically takes 5 steps in about 5 minutes. Let's get started. As with previous sections, we're going to take a bird's eye view of the process. And if you want further detail, we'll post another video that will show a full commented step-by-step overview. We're going to be using ExactFlat for our 3D to 2D conversion. The workflow steps are shown on the right-hand side. Remesh, flatten, optimize, add features, and export DXF cut file. The first step is to optimize our mesh for flattening. To do this, we can use ExactFlat's uniform and adaptive remeshing tools. These tools alter the number and size of the polygons in our model. Optimizing the mesh will help generate more accurate 2D pattern geometry and decrease the time required. As you can see, remeshing is fast and it's easy to adjust the tolerances and mesh element settings. Looking at these results, we have a great mesh that will be perfect for the next step. Once the mesh is optimized, we can flatten our model. To do this, we select the Tools tab of the ExactFlat toolbar. Then, we select the Flatten icon. Next, we rectangle select the part and hit Enter. Now we have our initial unoptimized flat patterns. The colors give visual feedback to areas of strain and sag. Red, orange, and yellow being areas of higher strain, black being areas of sag. White is neutral with neither strain nor sag. The cross marks at the edge indicate areas where the material is folded or wrinkled under itself, and these areas will need to be smoothed before optimizing. We'll use our fracture algorithm to dewrinkle the edges. You will notice that the fracture algorithm also eliminates a great deal of strain. These are initial flat patterns, and we must still optimize fit. To do this, we first assign specific material types to our model. These material types assign engineering characteristics, which alter how the patterns deform under strain and sag. When assigned, we are ready to optimize our patterns. The optimizer searches for areas of strain and sag and attempts to eliminate both, just like a real pattern maker, but faster, up to 1,000 iterations per second, and that is one reason why it is so accurate. You can see the optimizer redrawing the individual mesh elements and the boundary shape of the patterns to eliminate strain and sag. When complete, we can review the results. In this case, there is some residual sag indicated by the areas shown in black. We can now use our global target strain to introduce strain into our pattern pieces. How? We can select for the desired amount of strain. For example, if we set our desired strain to 1%, algorithms will deform and shrink the pattern piece such that the material will need to stretch by a factor of 1% in order to fit. And we can easily adjust the amount of strain to desired values. Because this is a compression sleeve that is intended to fit tight, let's go ahead and run the optimizer again. This time, let's introduce 2.5% strain. To do this, we first select a grain line, then entered a desired strain value for each pattern piece, and lastly, run the optimizer. You can see now that the patterns are virtually strain and sag free, exactly as we have intended. All that remains to do now is to add any desired features, such as notches, seams, or tracing points, and then create a DXF file. This DXF can go to the cutter or into your 2D patterning tool of choice for additional finishing. And there you have it. This concludes part 3 on how to convert your 3D CAD model to perfect 2D flat patterns. To recap, in step 1, we scanned our body part. In step 2, we processed the scan and converted the scan to CAD. And in step 3, we flattened our CAD model from 3D to 2D to create cut-ready patterns. This is ExactFlat Scan-to-Pattern, and we'll show you how. Thanks for watching. If you want more, there are other videos on other parts in our series on how to triple your pattern making in 3 easy steps using ExactFlat Scan-to-Pattern. It's the faster, better, cheaper, and easier way to create patterns for all your products. You can also contact us at your convenience for a demo or to learn more. We'll show you how.